I'm happy to be here. Unfortunately, I'm not in Halle, but I hope I can in this way tell you about recent advances and challenges that we face for going towards semiconductor spin qubits. Can you all hear me? Can you hear me all right?
Yes, it's fine.
Great. Okay. Great. So if you have any questions, please stop me, and I'm happy to also answer after the talk, of course. Okay, so I'm just want to, I think because this is probably quite a mixed audience, I just want to give you an introduction into the field, and then also try to give you some of the insights that we have gained over the years, and also what is the state of the art for semiconductor-based quantum information processing. Okay, so maybe you know, I'm going to start with something different, which is superconducting qubits. And so maybe you have seen this result from 3 years ago from Google, where they claimed that for the first time they have achieved a quantum computation that is impossible or practically impossible to reproduce with a classical computer. That's what they called quantum supremacy. Some people call it quantum advantage. And I want to, you know, kind of, this is maybe a vision. That's actually what we want to achieve. We want to build machines that can do something that you cannot do with conventional computer hardware. And so what you, I'm sorry, so I should go back. So what you see here on the lower right, maybe I have my cursor. So this is the chip that they're using. This is about 1 centimeter big. And it contains superconducting circuitry, so it has to be cooled. And what you see on the lower left is the CEO of Google or Alphabet. And next to him, you see a cryostat with a lot of wires. And so the cryostat is because they have to cool this system to below 1 Kelvin. And all the wires are because you have to control these qubits with electric pulses. I mean, you see also, I guess, some electronics racks in the back, and actually that's one of the big overheads we have currently with quantum computing. It's actually a big problem to scale these kind of systems. That's definitely not what you want in a normal computer. What you also see is that the list of authors, at least if you're at the university group, I'm a theorist. We usually publish papers with a few authors, but even my experimental colleagues publish papers with not that many authors. And so, but at Google, I think they think this is still a small team, and if they really want to make further progress, I guess they can do so. All right, so let me just tell you briefly what they have actually achieved or what they have claimed. So first of all, I guess most people know about quantum computing, but still, I'm going to give you like a 2-slide introduction into quantum computing. So basically what you have is a problem. Let's say you have to factor a big number. And then what you do is you can store this number. And in the end, what you want is the prime factors of this number. That's a problem which is very hard for classical machines. And what you can do, what Peter Shor told us in the 1990s, is that what you can do is you can store this number in a big quantum state. And then you have a machine which operates according to the laws of quantum mechanics. So it produces a big unitary map on this quantum state, and this produces an output state which you can then measure. And if the algorithm has worked, if the computation is successful, then this measurement will yield actually, let's say, one of these prime factors. So that's the idea. And so this unitary, of course, you can, the question is, how do you actually realize this? And these unitaries, as we know, they are produced by the quantum dynamics, by the Schrödinger equation. And so there's a certain Hamiltonian here, which governs the dynamics of our computer device, of our quantum register. And we have to choose this Hamiltonian in such a way in order to produce the right unitary. I mean, that's the unitary that, let's say, Peter Shor has given us, is given us by the prescription of the quantum algorithm that we're trying to perform. And so what this is actually a very complicated, high-dimensional, or you could say many-body control problem, which is very, very difficult because you would have to design such a Hamiltonian, and that's actually very difficult. But if you think about how computing works also in a conventional case, it's not that you make a new machine for every algorithm. We have universal machines, and actually they are also built up from universal elementary devices. And so that's also, that was found also in the 1990s, that this you can also do with quantum hardware. So you can build up quantum hardware from elementary building blocks called quantum gates. And so then you have these diagrams, which, so this is when you look inside the machine. And actually for physicists, this is basically a space-time diagram. So time runs from the left to the right. And space basically means, I mean, we're just looking at sort of a linearly arranged quantum registers. These lines here, these horizontal lines, are qubits as they propagate through time. And then there are some actions you can take on the qubit. Let's say this blue box here is something that happens to this lowermost qubit. This is a 1 qubit gate. So it does something on 1 qubit. And then there are also gates that couple more than 1 qubits. Let's say these 2 qubit operations. They are in red here, and they do some computations on 2 bits. And of course, you need to compute with at least 2 bits in order to make a computation. So these are the qubits. I already said all that. And so basically an important early result of the theory of quantum computers is that you can do anything from these elementary operations, just like in classical computation. So we can basically, as physicists, we can think about how to make good qubits, how to understand the physical properties of qubits, and also how to implement these elementary gates. And then in principle, we're done. Of course, it's a big engineering problem then to integrate all this and to scale up and do many of those gates. But basically, we first need to understand the working principles of such quantum gates. And here's an example. I think it's a very standard and important example. Is the so-called controlled NOT gate or CNOT gate. It operates on 2 qubits. One is called the control qubit C, and one is the target qubit T. And what it does, basically, it flips the target qubit. It performs a NOT operation, an inversion on the target qubit if the control qubit is in the state 1. So the qubit can be in state 0 or 1, just like a classical bit. But we will see that it can do more. So basically, if the control bit is 0, for example, and the target qubit is also 0, then as long as the control qubit is 0, nothing happens, But if the control qubit is 1, then the target qubit is flipped, as you can see here. Then the output of the target is 1 if its input is 0. Now, what's special about quantum mechanics, of course, as we all know, is that quantum systems can exist in a superposition of basis states. And so these 0 and 1 computational basis states, they are just quantum mechanical basis states of a 2-dimensional quantum system or a 2-level system. And I will be a bit more specific later on. So this qubit can be in a superposition of 0 and 1, or the bit can be on and off at the same time if you want. And so what then happens is that you have to, this has to be a unitary operation. So in particular, it's linear. So what you will produce is the output for the case 0 and the output for the case 1 at the same time. So you will produce a superposition of corresponding outputs. So this looks as follows. So now I cannot write the states of these 2 qubits separately anymore. Either the control was 0 and then the target is also 0 because it hasn't been flipped, or the control was 1 and then the target is also 1 because it has been flipped. And you see this state cannot be written as the product of the state of the control and the state of the target. So it's actually a very correlated state, and we call this quantum entanglement. So this is a very important property of quantum mechanics, that systems can be entangled. If you wish, the state of the complete system cannot be described as kind of a list of the individual states of the parts of the system. And this holds true also for a quantum computer. So basically, you cannot give a list of the qubit states. You have to give the entire state of the entire quantum register of these 2 qubits in this case. And then this is actually what gives the quantum processor its power, its superiority over classical machines. So this entanglement is a very important quantum mechanical concept. So basically, we try to teach this to students, and we try to make a new curricula, new degrees in quantum engineering and so on. But some people think we should teach this even earlier, and you can buy books when you actually teach this to your kids. All right, so I gave you this one example of factoring numbers, and actually this is an important example because it proves that you can do a quantum machine can perform hard tasks efficiently. But of course, you can ask, is this factoring really important? It's mostly important for breaking codes, and maybe if you're interested in doing something constructive, maybe there are other things than factoring. And actually, there are definitely a number of other tasks for which quantum computers could be useful. One of them is simulating other quantum systems, because this is something which is really hard on classical machines. Once you have strongly correlated systems, these simulations become hard because of the exponential size of the Hilbert space, essentially. And the idea that Feynman had in the 1980s already, and which sort of gave the initial impulse to develop quantum information theory and quantum computing, is to use a quantum system to simulate another quantum system, because quantum systems obviously can simulate themselves, and so they can, if you engineer them properly, they could potentially also simulate other quantum systems. And so this is, I would say we live in very interesting times, and this has been realized already 5 years ago on a very small scale. For instance, here in this work from IBM, where they looked at biatomic molecules, and they tried to simulate with very few orbitals the ground state of these small molecules. And of course, this is now being developed and scaled up and so on. So maybe coming back to this Google experiment, I'm not sure how many of you have read the paper and thought about what they actually did. So maybe I'll give you a quick summary. So here's a map of their processor. These gray crosses are the qubits. These are superconducting qubits, and these blue elements and their couplers. So they couple pairs of qubits. They had a bit more than 50 functioning qubits on their chip. And what is really a big achievement is that this is a fully programmable quantum computer, unlike other earlier devices. And each gate has a fidelity of over about 99%. So that if you perform one of these elementary quantum operations, the probability that it fails is less than 1%. That sounds, on the one hand, that sounds nice, but actually, if your PC was like that, that would be totally crap. I mean, you could never use such a thing, because of course, if you do many such operations, the error accumulates, and very soon, after only a few hundred gates operations, your output would be complete garbage. So this is actually not very good yet, but it's because these things are hard to build. This is a big achievement, and what it allows us is to perform small computations that don't have too many elementary operations in sequence. What Google demonstrated in their experiment is something that they say is practically impossible with the best classical computers. So this is really they compared with the best supercomputer that people have in Oak Ridge, for instance. And Google estimated that for the computation that their quantum computer took about 3 minutes, it would take this supercomputer about 10,000 years. Later on, IBM, which are competitors, Google in terms of quantum computers, said, okay, well, we installed this supercomputer and we know how to use it properly. And if you do that, it takes only 2.5 years to do this computation. But still, I mean, 2.5 years versus a few minutes, that's still a pretty big achievement. What it is not is it's not a useful computation. It performs random programs and does statistics to prove that this is quantum and not just classical. But the main point I would like to make here is that these qubits, maybe you've already noticed, these qubits must be large. Actually, each qubit is about 0.5 millimeter big. And that's the reason why you can only put 50 qubits on a chip which which is 1 centimeter times 1 centimeter big. I mean, as you know, in classical devices, you can put billions of transistors on such a chip, and so these systems are really large, and that has to do with the way these superconducting qubits are constructed. I'm not going to go into that. That's not the topic of my talk. So what I'm going to talk about is a different implementation of quantum hardware, for which I will also report a working universal quantum computer. And so this is based on the electron spin in silicon or in general semiconductor quantum dots. And because these are really small nanoscale objects, this system is at least potentially much more scalable. So you can put much more hardware on a chip of the size of the superconducting processor. Such a device, such a universal programmable processor based on electron spins was demonstrated also recently, actually even earlier than the Google experiment in 2018. The reason why you might not have heard about it is that it had only 2 qubits. So, of course, you cannot do that much with 2 qubits. So this has been really, for the most part, a demonstration, just a proof of principle demonstration. This has the systems that people are able to control now with spin qubits have grown over the years. So at the moment, I think the most recent experiment that has just come out in Nature has 6 qubits. I'm going to mention that one more time later on. Also, it actually doesn't only matter how many qubits you have. It also matters how good the qubits are. So sometimes people announce that they have a chip with 100 or 1,000 qubits, and then I think it's always wise to ask how high is the fidelity of quantum operations. So, and actually, for the spin qubits, the fidelity of 2-qubit gates was not very high initially. It was only about 80%. And then it increased, and I will tell you a little bit what's behind that increase. And the latest results from this year are that we have 2-qubit gates with a fidelity, so a success probability of 99.5%. That's about the same as the most up-to-date superconducting qubits. So here's what I want to tell you about. I'd like to tell you a bit more what these spin qubits are, how they work, and then also some of the challenges that we have faced. One of them has to do with materials, actually, because there are nuclear spins in the materials people are using, and this is a materials challenge. And then I also want to tell you about electric control, because spins are objects that react to magnetic fields, as you all know, but we would like on a chip, we would like to control them with electric fields. And then I will tell you a bit more about this universal 2-qubit processor that I already mentioned. And then finally, maybe give you an outlook towards other things, other challenges that we have to solve. For instance, how to couple distant qubits. All right, so what are these spin qubits? Basically, the idea is that if you have a particle like an electron that has a spin 1/2, the spin degree of freedom has exactly 2 distinguishable states, spin up and spin down, and you can just identify them with the 0 and the 1 of your elementary unit of quantum information, the quantum bit or qubit. And then, of course, you need, you need to be able to address these qubits one by one in a register. So it's now used if you just have lots of electrons in a metal, for instance. I mean, you will not be able to address these qubits individually. So what people do is use semiconductors, deplete, let's say, a 2D electron gas completely. So you have no electrons around, and then you start accumulating electrons again with accumulation gates. So this is, for instance, something you see here on the lower left. This is an electron a micrograph of a device which is based on silicon. It has metal gates, and it has accumulation gates and depletion gates in a 2-layer architecture. So you first accumulate some electrons, and then you deplete again some regions, and what's left are quantum dots that contain only few electrons. ideally down to one electron, and the spin of these electrons you can then use as qubits. And maybe an up-to-date result has been demonstrated, just been published in Nature by the group of Lieven van der Sijpen at TU Delft. They have 6 spin qubits here in a row that they can individually control and couple, and they have a 6-qubit universally programmable spin-based quantum processor. So there are, but actually, and that's the kind of spin qubit I'm going to be talking about for the most part today. But actually, just to give you a little bit broader context, there are many different types of spin qubits that you might think about. You could use the electron spin in such semiconductor structures as I just mentioned. You could also try to use nuclear spins, for instance, of phosphorus donors. They also have spin 1/2, and they're even more long-lived, more coherent, but they're a bit harder to access. Then, of course, instead of electrons, you might use holes, and there are good reasons for that. And this is something that's become very fashionable these days. And I will tell you later why holes are also a really good contender for spin qubits. Then, of course, there are other systems like wideband semiconductors or even insulators where you have defects that have spins, and they can be very, very well isolated from the environment and be very have a very high quality, but then maybe a bit harder to scale. Also, in principle, one could imagine using spins in 2D semiconductors, such as transition metal dichalcogenides or gapped graphene. And so these are all interesting directions. We have done some work on all of these directions in my group on the theory side, and we've collaborated with experimentalists on most of these things. But if for the sake of brevity, I'll concentrate on electron spins in 3D semiconductors for this talk. Okay, so this is what such a processor would look like. You have a series of quantum dots with individual electrons. So you load them with individual electrons. They have a spin. These are the qubits, and then you can couple them. You can sort of modify the coupling between them by these electrodes between the quantum dots, and they basically the virtual hopping between these quantum dots can then lead to exchange coupling between the spins. So this is what we model by this first term in this exchange Hamiltonian, and then there could be some way of locally addressing the spins with a local Zeeman effect, with a local magnetic field. And such exchange coupling has been shown that they produce 2-qubit gates. And I mentioned already the state of the art is that this can be performed with fidelities, with sort of success probability exceeding 99%. And these local Zeeman fields can produce single qubit gates, as I mentioned before, and these gates have even higher fidelities. And of course, you also and then if you have these two things, as I mentioned before, you could in principle do universal quantum computation if you can scale these things up and integrate them. What you also need is a good readout. So you have to measure the system in the end to get your result out. And this has also recently been demonstrated. That's actually not trivial. That holds also for superconducting qubits to have high fidelity readout. So what could go wrong? First of all, so I mean, basically 20 years ago, people managed to make quantum dots in materials like gallium arsenide, where the quality was so high and the control was so good that you could really put single electrons in every quantum dot. And so you have basically this system, you have just one electron, no other electrons that bother you. The problem is you still have other spins around. And the reason is that you have nuclear spins. So of course your host material is a solid that's made out of atoms. And for instance, in gallium arsenide, every atom has a nuclear spin, and your electron spins are coupling to these atoms via the hyperfine coupling, and this destroys the coherence of your qubits. And so that's bad. And so this is a materials problem for the most part. And so maybe just to summarize what has happened in the meantime, people have started out with gallium arsenide with lots of nuclear spins. The coherence time, so that's the time over which this superposition 0 + 1 would survive before it dephases. It completely collapses to a statistical mixture of 0 and 1, where you would do classical computation. So this time was on the order of just a few nanoseconds. So this is called the T2 start time. And then in silicon, in natural silicon, so that's basically the big step that people took 10 years ago, that they started working with silicon because it consists, for the most part, of an isotopically, of an isotope that has 0 nuclear spin. You can reach coherence times immediately with natural silicon of 1 microsecond. And then, of course, you can purify silicon. You can get the silicon-29 out. Silicon-29 has spin 1/2, and silicon-28 has a no spin. And so you can get out the remaining 5% of silicon-29, and you can reach even higher, 2 orders of magnitude higher coherence times. You can actually extend this thinking, looking at the periodic table, and see which elements have nuclear spin-free isotopes and how abundant they are. And you see, if you take 3-5 semiconductors, you're out of luck, because they all have all of their stable isotopes have nuclear spin. But in the 4th column, you have carbon. I mean, these have even numbers of nuclei. They usually have a high abundance of a spin-free isotope. And so, for instance, carbon is very nice. It has 99% Z12, which has no nuclear spin. That's why we think that diamond and graphene are nice materials for solid state-based quantum information processing. I already mentioned silicon. And of course, there are other combinations, silicon carbide, for instance. And also germanium is a promising material. And then there are others, like I mentioned the 2D semiconductors, transition metal dichalcogenides. They can also be isotopically purified, basically. So these are all promising materials. But at the moment, I would say silicon is really the workhorse of spin-based qubits, and some people work on germanium. But I mean, there are also problems if you work with these materials. For instance, I mean, the band structure of these materials is usually more complicated than the band structure of simple 3-5 semiconductors, where you just have a single valley in the conduction band, like in gallium arsenide. So you fill up your Fermi sea from the gamma point in the center of the Brillouin zone. And if you make a quantum dot, basically, if you have quantized the motion, so basically you have an orbital level splitting, all that's left is the spin degeneracy, and that's of course exactly what you want for a qubit. And if you couple these qubits nearest neighbor with nearest neighbor hopping, what you will get is the standard just Heisenberg exchange coupling, which produces our elementary 2-qubit gate. So that's all very nice. But in silicon and germanium, for instance, you have more than 1 minimum in the conduction band. If you make a quantum dot out of these materials, you will have an additional orbital degeneracy, the so-called valley degeneracy. And so you have another degree of freedom that is sort of disturbs the qubit operation, and it's also at low energy. And actually, if you compute the exchange coupling, what you will get is something like this, where the spin couples to this valley degree of freedom, which is actually, from a physics point of view, very interesting. But from a quantum computing point of view, that's not so nice, because that's yet another degree of freedom that somehow disturbs your system. All right, what else could go wrong? So let's say you work with silicon, there are no nuclear spins, and but the other problem is, I mean, I said, okay, now we need these local magnetic fields to control our spins, because spins couple to the magnetic field. They have a magnetic moment, they don't have an electric dipole moment intrinsically. So that's how you would do it, but actually that's very hard to do on a processor chip. What you really want is you want to control your qubits via electric fields. I mean, that's very easy to do. So that's the next thing. So okay, so let's back up. If you have a spin 1/2, let's say, and here's the 2 energy levels, spin up and spin down. If you apply a sufficiently large magnetic field here, BZ, and then you can apply an oscillating magnetic field perpendicular to this fixed magnetic field, and use electron spin resonance to rotate the spin. So that would be something that you could say, well, that's a single qubit gate. Let's say just flip the spin, you could do this ESR. And actually that has been demonstrated, but that's very hard to do. Local oscillating B fields are hard to achieve on a chip. And what would be much easier, as I mentioned, is local oscillating electric fields, because you would just apply basically an AC voltage to your electrodes that you're also using to define your quantum dots. The problem is, as I mentioned, electron spin has a magnetic rather than an electric dipole. So the way out here is, and of course we've in the previous talk heard a lot about spin-orbit coupling. Of course, one of the resolutions here would be to use spin-orbit coupling. And that actually has been done. I mean, gallium arsenide, for instance, the spin-orbit coupling is fairly strong, and so you can easily do that. It has also been done in silicon, but actually it's harder because silicon is a lighter element, and even more so carbon. So in these materials, it's actually not so efficient to use spin-orbit coupling to drive the spin electrically. It can be done in germanium, so that's one of the advantages of germanium. In silicon, what people do is because of the lack of natural spin-orbit coupling, people introduce synthetic spin-orbit coupling by placing small micromagnets on their chip, which produce a magnetic field gradient. And if your electron now moves in this field gradient, you excite them electrically with an AC electric field, they will oscillate in the quantum dot. They will just shuttle around, and then they will see effectively an oscillating magnetic field because they're in a magnetic field gradient. And that's how these high fidelity single qubit gates have been achieved. You can even increase this effect by with the so-called flopping mode spin qubit, where you have two quantum dots. So you have a double well potential, which you fill with just one electron. So the electron can be on the left or on the right. And this whole system sits in a large or in a fairly large magnetic field gradient from a permanent micromagnet. And then you can basically you can control your spin if the system is in the symmetric case. I mean, this is this picture here where the electron can go left and right. You can electrically make it oscillate between the two quantum dots, and then it experiences a very large magnetic field gradient with a large amplitude, and you can efficiently drive it. And you can, if you don't want the coupling, you can park it in one of the two dots, and then this coupling is actually switched off. And so there's a little theory. I mean, maybe I'll go through this quickly because I don't have so much time. I mean, this is basically a spin qubit coupled to a charge qubit, the left-right degree of freedom. The coupling is provided by the field gradient. You can drive this system. So, you can look at eigenstates as a function of this detuning. You can drive the system, and what comes out, you can calculate the spin Rabi frequency. It's proportional to the charge Rabi frequency, so the frequency at which you drive the left-right degree of freedom, and then it's related to the tunnel coupling between the dots Tc and the magnetic field gradient Bx. And there's a sort of a resonant behavior, and this has also been tested then experimentally, and it leads to a very efficient drive of the spin qubit. So maybe I'll go on here. So this is, I think, sort of these are sort of the main problems that had to be solved in the last years, and so now we're at the point where we can really try to make this two-qubit gate more precise. And so there are various ways to operate this. You can basically just switch on the exchange coupling between two neighboring dots in a sort of adiabatic way, slowly, in a homogeneous field. And this works. This has been demonstrated. This is one of the earliest demonstrations of a two-qubit gate for spin qubits. It's limited by charge noise. And nowadays, people usually work with these magnetic field gradients because of what I just said before. You want electric control, and so then the control is a bit different. Maybe I want to tell you how this works. So this, I'm going to tell you now about two-qubit gates between spin qubits, and there are two different ways you can do it, either AC or DC. So what you have is two spins that are coupled by exchange coupling J. You can switch, I mean, this exchange coupling is controllable by this center gate VM. And then there's also a magnetic field gradient. So the two spins, SL and SR, experience different magnetic fields. There are two gradients, or the gradient can have different components. And so if you look at the energy levels of this system, just these two spins, you have 4 spin configurations. In an external field, they will split up. I mean, the parallel spins will split off, and then you have the anti-parallel spins that have total spin along the external field, which is 0, and they are degenerate. But now if you have a magnetic field gradient, they will of course also split up. And then if you switch on the exchange coupling, what happens is that these anti-parallel spin components will be lowered in energy. So while the exchange is on, these two states have a lower energy, and this means that they acquire a phase, and this can be used as a quantum gate. This is the so-called C-phase gate. This is also a universal quantum gate for quantum computation. So that's one way of operating your 2-qubit gate. There's another way, which is which we call AC control, where you do the same thing, but while the exchange is on, you also drive an AC electric field to one of the spins or both. And actually, I'm going to explain in detail, but this allows you to directly do a CNOT gate. That's what we call AC gate. Let me explain a bit further. Okay, so you have these different components of the gradient. So one of them creates an artificial spin-orbit coupling. The other one distinguishes the resonance frequencies of the two spins for spin resonance. And then you can drive using the gates. And so again, if you look at this energy diagram, so if you switch on the gradient, we split up. So if you have a gradient and no exchange coupling, if you drive at one of these two frequencies, you're always going to drive either the left or the right spin unconditionally. So it's not a conditional gate, it's just a single qubit gate. This is useful because you can do single qubit gates on the left and right qubit individually, but you cannot do a two qubit gate. So if you then switch on the coupling, there's a specific frequency to rotate, let's say, the left spin only if the right spin is in the state 1. So this is a controlled NOT gate, and this is a unique resonance. So you will not drive any other resonance, and so this is a CNOT gate. And so that's something that we predicted and analyzed, and also that was what was performed in 2018 in the group of Jason Petta, then still at Princeton. So this is the device that they actually used. It's a double quantum dot in silicon. So this is the theory for the probability of the target spin to be up. I mean, I'm going to go a bit faster here. This is the experiment. And you see there's qualitative agreement. You see that gate time is about 130 nanoseconds. The visibility is not 100%, it's just 80%, and that limits the gate fidelity here. And then there's another limitation, which is that there's off-resonant dynamics. So actually what I told you before was not entirely correct. If you drive a resonance here, which is unique, of course you drive the other transitions off-resonantly. So there's going to be a small amplitude, high frequency oscillation, also if the control qubit is 0. And this leads to errors, but these errors can be corrected, and we proposed a scheme to do that, which we call synchronization of gates, which means that you choose the ratio between your coupling and your drive strength in such a way that while the resonant rotation makes a pi rotation, so just a 180-degree rotation, the off-resonant rotation does a multiple of 2 pi. It just goes around a few times, but comes back to the same point. This is what we call synchronized gate. And this is what has been used in one of these very recent demonstrations by the group of Sego Tarucha to reach even higher fidelities, exceeding 99%. And if you read their paper where they show us AC CNOT gate, you will see that the ratio between their exchange and drive strength has is a square root of 15. And if you don't know our theory, you will not understand why this is square root of 15. It's just a special case of our synchronization condition. There are also DC gates in Delft. They are doing DC gates with very high fidelity, which is also nice. And in both cases, there have been small applications, small algorithms have been run. And in the case of Delft, they have done also a small quantum simulation, hybrid classical quantum algorithm simulating a biatomic molecule. yeah, I think I should wrap up soon. So of course, if you plot the gate fidelity as a function of time, and this is a logarithmic plot here, you see that, okay, there are DC gates, those are the green dots, there are AC gates, the red dots, and they have increased tremendously over time. And of course, it's tempting to draw a line. So this would be some kind of Moore's law of spin qubit fidelity. I don't know whether you can completely take it seriously, but I hope, of course, that this fidelity will further increase. Maybe I'll skip this and maybe just say a few words about the last topic, then I wrap up. So basically, one thing that we'll still have to do is a long-range coupling. And the problem is that if you look at this Hamiltonian, it couples nearest neighbor spins. But if you look at the circuit, you will see that you have to also apply 2-qubit gates between any pair of qubits, no matter how far apart they are. And so how do you do this? And the one idea to do this is to combine technology from superconducting circuits, so superconducting qubits, where they use resonators, basically small microwave cavities, planar cavities made out of superconductors, to couple distant qubits, and then combine them with these very highly coherent and small scalable spin qubits. And so the idea is to then use cavity-mediated long-distance interaction. And I think I'll skip this. So there are different types of qubits, and maybe I'll just skip ahead and show you the latest results. So basically, maybe I'll show you this. So basically, so this was achieved in also 5 years ago, basically to couple such a flopping mode spin qubit, so a double dot with a single electron, to a microwave cavity based on superconducting circuits. And so that the telltale sign of this coupling is the so-called vacuum Rabi splitting. And so this is what you see here. This red is a theory, and this bluish plot is a corresponding experiment. This is a cavity transmission experiment where you see basically you see the splitting of these vacuum Rabi peaks. And so basically what was achieved here is that the strong coupling regime of quantum electrodynamics, cavity quantum electrodynamics, has been reached, where the coupling is stronger than both the cavity loss rate and the qubit decoherence rate. Of course, as next steps, we want to couple two such qubits coupled to the same resonator mode. And so there's theory for that, and people are working on these experiments. So maybe that's just, I think, my last slide. So there are experiments here. This is an experiment from Princeton, the first one, where two spin qubits have been coupled simultaneously to the same microwave cavity, and such a combined vacuum Rabi splitting has been seen, which proves that both of them are simultaneously coupled. Then there has been an experiment this year from Delft, where this coupling has been shown also. And then actually what's also interesting, I think, is that you can use such coupling to couple different types of qubits. So if you have, of course, you can couple superconducting qubits to superconducting cavities, and now you can also couple spin qubits to superconducting cavities, which means you can now couple indirectly the spin qubit to the superconducting qubit, and you could use the best of both worlds and make hybrid quantum systems. So that's also a very interesting development. So let me summarize. I think my time is up. What I've shown you is that we have local CNOT gates, so the fundamental quantum gates for spin qubits have now achieved in excess of 99.5%. That's very good. And in the future, people will, of course, increase this fidelity. This is a combined theory experiment effort. We have to decrease crosstalk. I've not talked about this. Now, I think another topic is to really improve the single spin photon strong coupling between spin qubits and microwave cavities in order to achieve in the long run these long distance quantum gates. You can also use it to read out qubits, a couple different kinds of qubits, which could also include nuclear spin qubits, which are very long-lived. A big remaining problem is charge noise. So all these systems both superconducting and semiconducting systems have charge noise, which seems to be almost universal, and it affects the coherence of all these qubits. One interesting development that I mentioned is that people can use holes in germanium. Germanium has also low hyperfine, low nuclear spin density, and it doesn't have this valley degeneracy in the valence band, and it has relatively strong spin orbit, which can then again be used for electric spin control without these micromagnets, which could be an advantage. Finally, I'd like to mention 2 review articles. The first one is about cavity qubit spins, and the second one is about spin qubits, which is going to come out in Reviews of Modern Physics soon. And I also would like to acknowledge all my collaborators from Konstanz, and also the long-standing collaboration between our group and the Princeton group, which now moved to UCLA. So with this, I thank you for your attention, and I'm happy to take any questions you have.
Okay, thank you very much. Well, thank you, Guido. So we have time for some questions. Benabir, would you like to ask a question? But you might need the microphone. Or you could shout.
Hello.
Hi.
I have 2 questions. One is why there are not many algorithms, like there are only like every work is to produce source algorithm or simple 2-qubit operation. Why is not like much progress up in terms of algorithm after this 1996? And second question is this: when you discuss the realization of the CNOT gate, at some point of time you said this is a NOT gate but not very controlled. So in that case, is it like simple NOT gate, but it has to be unitary, right? It has to be controlled NOT, right?
Okay, so let me take the second question first. I think you're saying you're talking about this, right? Yes. So where this one, right?
Yes.
Yeah. So here, if you have a magnetic field gradient, but the 2 spins are not coupled, so the exchange coupling is 0. In that case, you see that these frequencies, this FR frequency appears twice. So the distance between these 2 and the distance, I'm not sure. So yeah, you see it here. So you see this FR, these are exactly the same resonance. So if you drive at this frequency FR, you will rotate the right qubit no matter what the state of the left qubit is. If the left qubit is down, you will drive this transition. If the left qubit is up or 1, you will drive this transition. And so it means it's just a single qubit gate of the right qubit. No matter what the other qubit is, you just rotate the right qubit. That's a single qubit gate. That's useful, but it's not a 2-qubit gate. If you have the exchange coupling on, and you drive this frequency, that's a unique frequency, doesn't occur anywhere else. And so you will just drive this transition. So in this case, you will rotate the left spin only if the right spin is in the state 1. If the right spin is in the state 0, you will be off resonant. You will not drive it because this frequency is now different.
Okay, thank
you.
This
down here, which is now different. And your other question, okay, so about algorithms, I mean, that's a very good question. I would say, actually, there has been quite a lot of progress in developing new algorithms. It's just that these algorithms are not that known. I mean, for instance, there's an algorithm for solving linear equations, big linear equations. This has actually applications in machine learning and a lot of other areas. And there are algorithms for optimization problems. And there are generalizations, of course, of the Shor and Grover algorithms. So I think there is progress, but of course this progress is, maybe I'm also a bit impatient, right? It would be great if there are even more algorithms, because we know that these quantum computers would not be universally useful, machines. They're not basically better than classical machines for every problem, so only for these specific algorithms. And so I think there is progress. I mean, I would say also for me, this quantum simulation of complex systems is one of the most promising, because that's quite universal.
Thank you very much. We have a question from Joyce.
Hello, hi.
Hi.
For the very wonderful talk, I have a question about how these spin qubits, if they were to couple to the microwave field in the cavity QED regime, how does that work in terms of doing a computation? Because there's one, yeah, how do all the qubits get entangled with each other? And how could you have programmability of the individual qubits if they were then all coupled to the same?
Oh, okay. Oh, okay. That's a great question, and I'm sorry I didn't really explain that because I was rushing over this. So here's sort of I mean, maybe just look at this picture. So we have this. Actually, that's the beauty of this flopping mode spin qubit. So you can switch on and off the coupling by biasing this double quantum dot. If you bias it very asymmetrically, the electron is stuck in one of the two dots. And so basically the electric dipole is very small. It's just because the electron cannot move. And so you can think of this electron as an antenna. And so basically it doesn't couple to the microwave field much if you make this very asymmetric. And only if you make the double dot symmetric, the electron can move back and forth. It can sort of slosh back and forth, and it has a big electric dipole, and that's when it actually couples to the microwave field, and that's when also the spin couples to the microwave field. So you can switch this coupling on and off. That's the upshot. And so what you would do in this case, you would, let's say you have many of these qubits coupled to the same resonator mode. You would only switch on the coupling for two of them, and then they would be able to perform a quantum gate. I mean, that's one thing we showed in this paper is that you can then do some kind of 2-qubit gate over a long distance.
Okay, so it's not. Are there any plans to maybe scale that up to have more than two gates kind of working together, then coupled to the same resonator mode?
There are definitely plans. I mean, these experiments are not easy, but I mean, on the theory side, we definitely are looking into this. I mean, you could imagine coupling more than two, and then, what you would probably do, I think what I can imagine is that you have an array of qubits that is coupled locally. Let's say you have these strings of 6 or maybe even bigger. And then in addition, you put several of these modules into the same resonator, because you have to see that this, I don't know whether you can see it. That is another thing I skipped. So these resonators are much bigger than the qubits. Well, I'm not. So you could put many of those spin qubits into the same resonator. Yeah, you don't see it here. I think I don't have this. I don't have this slide. But basically these resonators can be, they can be basically they can be a millimeter long or even longer. And these spin qubits are, let's say, 100 nanometers. So yeah, you don't see it here. I thought maybe I had a.
Put many of these qubits within the cavity, but I'm not sure how they're supposed to sort of work together or interact with the electromagnetic mode, and what function could come out of that kind of interaction.
So this has been demonstrated for a single qubit. So I wanted to show you this picture, but I didn't find it. So this has been demonstrated 5 years ago in several groups. Yeah. So at least I can give you the references. I don't have the picture. So here these are 3 references. So this is the Princeton work where they showed that you can couple one such flopping mode spin qubit to the quantized resonator mode of a superconducting cavity. And actually they already, in this experiment, they had 2 coupled to the same cavity that just didn't use both of them. And there's another experiment which basically does the same. And then there's another experiment from Paris where they used not silicon but carbon nanotube. So this has been done, and then I mean these other experiments I showed, I flashed briefly. Sorry, these experiments. So in these experiments, what people did is they actually coupled 2 qubits to the same resonator mode. So it's basically you have this big coplanar waveguide, and you can put either you put these qubits directly inside, and then they see the electric field of the waveguide. It's like it's sort of a 2D or split open coaxial cable, and basically the qubits are then experiencing the electric field of the microwave mode. Or you can connect with a gate. I mean, basically you connect one of the plunger gates to one of the ends of such a resonator, which also has basically then the quantized voltage.
Okay, well, thank you very much, Guido. I think unfortunately we've run out of time for any more questions. So we much